Thank you everyone for coming here. And it's so this is actually a very applied work that I started as a master student, and it's about like a semi-parametric approach for analyzing some high-dimensional non-stationary autocorrelated electrical cardio diagram data. It's a type of time series data. It's actually like we apply these methods on this type of data, but the methods is actually have some is good for universal time series, like not just limited to ECG data. So yeah, so it is well established in the literacy that the ECG data is some type of data that is have some behavior of like non-stationary and non-linear like properties. And as some like the advancement in the modern data storage techniques, this ECG data is more than often like behave like really high dimensional. So as a consequence, some conventional time domain algorithms is really struggle to effectively describe this kind of intricate dynamics of the ECG data. And yeah, these are two like type of ECG that like we're dealing with. The first one is the normal patients, and the other one is some patients like have some premature ventricular like disease. And so to start with, the so-called stationarity in the time series is it's like some kind of statistical properties of a time series remains asymptotically constant over time. But if you are dealing with some real world data, you will notice that it's actually quite demanding conditions, because usually most of the real world data is we will have this some non-stationary behavior in their or some time varying parameters in the model. So our main goal in this project is actually to handle this kind of time varying parameters with some statistical model. And this is our model, and it's quite a very simple model. The observed data YT actually follows a mean shifted model, like it's very classic in time series. With the time varying mu, is a function mu t plus an error term, and this error term actually follows an autocorrelated structure with a time varying sigma t, time varying variance, and this evidence t is an IID Gaussian. You can with a constant variance. So in fact, this mu and sigma cannot be some arbitrary functions. We have to actually impose some conditions on those functions. For example, we define this u out when it's outside the range of 0 and 1. We will make it like a constant and equals to the edge point of the range. And when it's inside the range 0 and 1, we will impose them to be differentiable and have some bounded derivatives. So the reason why we need this kind of like a smoothness conditions on the function is that we have to like impose this so-called locally stationary property on the data we're dealing with. So this is actually like a direct result of the Lipschitz continuity of the functions, where you have this Lipschitz constant C mu and 6 sigma that from this kind of upper bound for the arbitrary time points inside the range 0 and 1. And so we actually like we define the parameters. We will define all these parameters as a function of in a rescale time framework. And for the real time index t, we can construct it as this sequence Tn, which is equal to u times n when u is a real number between 0 and 1 with these floor functions. So with this kind of representation, we can easily obtain like naturally follows like we can naturally obtain this the following uniform bound, like the supremum of the t, the difference between t over n minus u is lesser than this 1 over n. So with this uniform bound, we can actually form these so-called the locally stationary properties of our functions, which means that so when the number of observation n grows increase, we can observe more and more observations around the at the same time around the time point u. And yeah, so this type of so-called locally stationary properties is actually very, very crucial for us to estimate these time varying parameters on a finite grid. And that directly leads us to the method we're using in these projects, which is the B-spline. And so usually people use a kernel smoother to do these kind of estimations, but compared to kernel smoother, B-spline have these several advantages, like it's capable of handling some missing observations, and it also is very robust against some model misspecifications if you have some a good model selection criteria. And so actually we're not just using the B-spline in this project, but we are using it in a generalized least square framework. So as you know, for the generalized least square, we have the most important key component is the covariance matrix, actually the inverse of the covariance matrix. So in this project, we actually estimate the spline coefficient of the time varying mu, and after that we will obtain so-called residuals, which follows an autocorrelated structure. And we since we structure our model in this way, we can estimate this autocorrelation coefficient using the weighted least square methods. And once we obtain this estimation of the autocorrelation coefficients and the sigma t, we will use that to construct the estimation of the inverse covariance matrix, also called the precision matrix, and we will use that to update our estimation of the mean square, the time varying mean functions. And beside that, we actually use the so-called generalized BIC with prior this kind of model selection criteria to determine what kind of what's the optimal order of the P, like what kind of ARP model we're using for estimating the inverse covariance matrix. And so in the simulation study, we will actually show that this generalized BIC with prior will outperforms the traditional BIC, especially with small sample sizes. So this is our model, right? As we mentioned before, it's time varying mu plus error term xt, and this actually follows autocorrelation functions with a time varying sigma. And as we mentioned before, the sigma and the mu is bounded, is some bounded functions over time with some smoother conditions. And we estimate this time varying mu using the spline, using the spline estimations, where this Sj mu is the base functions, and the beta j is the estimated spline coefficients. So as we mentioned, we use the generalized least square estimation to estimate the spline coefficients, and the most important part here is the inverse covariance matrix, and we will update it in each iterations. So for the estimation of the sigma t, the 2008 paper used the kernel estimations for the estimation of the sigma t, and they actually provide us some rigorous proof for the asymptotic properties of the kernel estimations. But instead, we use the spline estimation in this study to somehow get in line with what we are doing with the time varying mu. And we actually apply this B-spline smoother on the absolute value of the residuals to get this sigma t. So about estimating for the AR coefficients, AR model, we look at the quasi likelihood of the ARP process. Like for simplicity, so here we just assume constant. We assume the error term to be have like a constant variance, and so the x here is the response, the response value. Like here's the original time series, and this z is the design matrix. Where for estimating ARP model, it's usually just the lag p matrix of the original time series, and this phi here is the coefficient of the error coefficients. So if you write out the log likelihood functions, is the log likelihood function for the ARP model under the quasi likelihood is like this. And you can just simply solve it using some ordinary least square estimator, like this C transpose Z, the inverse of C transpose Z times X. And with this estimation of AR coefficients, we can have the MA estimation for the sigma squared, which is in this form. So we further, and the most important part here is that we further denote the two matrices, AN, which is the Hessian matrix of the log likelihood, and BN, which is the covariant matrix of the Z transpose X. And this is actually the outer product form of the Fisher information matrix. So in an ordinary least square estimation like setup, we can estimate these two matrices using like using the following. Like AN hat is equal to sigma hat square times Z transpose Z, and BN hat square is BN hat is equal to Z transpose times the diagonal entries of the Hadamard products of these residuals times Z. And so what's happening here is that this AN is actually the best covariance matrix of Z transpose S under the best misspecified model, and this BN is the true covariance matrix of the Z transpose X. So following some regular derivatives of the MLE theory, you'll find that AN is actually equal to BN if and only if the model is correctly specified. So we actually follow some already like some result from this paper.
So maybe I missed it. Can you go back to the slides? What's the quasi likelihood here?
Oh, just means like we don't like impose some structures on the epsilon t. So epsilon t is just we assume to be IID normal distributed, like a multivariate normal.
Okay.
So usually it's like usually to estimate this ARP process, you have to like there's some autocorrelated structures inside, but for a quasi likelihood estimate, we just assume like epsilon t is just a multivariate normal.
Oh.
Yeah, it's like a yeah. So yeah, as I said, like follow this there some of the result of their 2016 paper. They define like this kind of a new model selection, generalized model selection criteria, using this so-called covariance contrast matrix HN, which can be estimated using the inverse of AN hat times BN hat. And the one we are using in our in this project is the generalized BIC with prior, because it's just plus the trace of this matrix HN minus the log of the determinant of HN. And the first part is just the regular BIC. So with this model selection criteria, we can actually formalize our estimation of the error coefficients, which, as I said, is following some weighted least square estimation, where this sigma zi is the weighted weighted matrix for the estimations, and follow some like textbook derivation. You will see that error coefficients you will have this kind of closed form solution. So once we get the error coefficient as well as the sigma t hat, we're going to estimate this inverse covariance matrix. And also like follow some like textbook derivatives. You will know that the inverse covariance actually can be decomposed into like into like the product of the two the other product of a matrix LK, which is a lower triangular matrix that had this kind of nice band limited manners like structures. Where the first P-1 row is actually the standardized partial autocovariance. And starting from the pth rows, the diagonal entries will be all one. And starting from the diagonal entries, you will plug in the autocovariance coefficients, the negative of autocovariance coefficients, and like just following this kind of band limited structure. So with this kind of like band limited structure, you can actually avoid some like repetitions in your calculation, and you can actually lower down the computation complexity of your calculations. So for example, like for some entries in the gamma, so actually for all the entries in the gamma ij, the inverse of gamma ij's, it's equal to 0 if the row index minus the column index is greater than p. And it will, for the diagonal entries, it will be equal to the summation of the phi k squared from k equal to 1 to p plus 1. And for all the like subdiagonal entries, it actually follow a little messy structure, but you can also like calculate that using some kind of a loop in your programming language. So what remains to be considered is the only like the 2p times 2p top left corner of the submatrix, like for this part. And by that, you can actually like reduce your computation complexity from n cubic to p to p cubic, which is it's a lot. It's a lot improvement. But for the above like derivatives, is only we assume like for some constant variance. But if your variance is time varying, just need to do some little adjustment where you can have your LKs equal to 1 over sigma t over n for the diagonal entries. And for the subdiagonal entries, you just plug in this extra fractions. And I didn't like print out the entire LK matrix because it would be too messy, but you can do it like you can just plug in these numbers and also get the value of every entries, and you just plug in the values in a band limited manners. So with all these components, we can finally go to the entire algorithms. So in step 1, we will detrain our observed data YT and obtain the error noise XT. And in the step 2, we will select the best error model using the general IBIC with prior. And then we will estimate the error coefficient using weighted least square. Then once we get the error coefficients, as well as the sigma t hat, we will plug into the definition of an inverse covariance matrix and get this precision matrix. And once we get the precision matrix, we will update our GLS estimator using this formula. And we'll keep doing it from step 1 to step 5 iteratively and until we reach a threshold. So the idea here is that like the better the estimation of the mu t, the better the estimation of the error coefficients, then which will result in a better estimation of the covariance matrix, and that will like contribute to the estimation of the mu t in the second iterations. So for the simulation study, like we kind of generate this kind of non-stationary time series model with p equals to 2, which is an AR2 model, and with this kind of like bell-shaped sigma t, which is as I mentioned, it should be a bounded smooth functions. And we kind of do like 100 replications and try to see like how the model selection criteria do like perform in this for this non-stationary time series. And we found out that the general IBIC with prior actually outperforms like every other like model selection criteria in this setting. But one important thing is to mention is that the performance gap between the BIC and GBICP actually narrows, while you have like a when you like the sampling frequency is increasing. See, like we have this 82 against 94, and here we get this 87 against 88. So yeah, that's basically the some result of the simulation study. And we then add this non-stationary noise to like a typical ECG trend from the healthy group, which is represented by this red line here. And so the red line is at actually the base, the true mu functions we have, and the blue solid line is the generated time series using the simulated noise. And we do the entire algorithms on this generated data sets. And this dashed line here is the 95% semi-parametric interval for our estimation. And you can see like the bound is actually very close. It's like we have like some like a good fitting performance using this generalized least square framework. And this is the estimation of the sigma square hat. Then we like so once we have this the spline coefficients, we store this kind of spline coefficients as well as the estimation of the sigma t. But and with some other features like the order of the p of the area coefficients. And we kind of do some simple clustering performance to see like if the dimensional the reduced dimensional feature matrix can preserve like most of the informations of the original data. And we do this kind of a comparison. And I would say like the performance is quite similar. Like some of the features like the data set will outperform the original data set, but not by very much. But the computational time for the feature selected data sets is actually much lower than compared to the original data set. So yeah, that's of my presentation. Thank you.
Any questions? I have a question. So we can go back to your algorithm slides.
Okay.
So yeah, I don't know. Yeah.
Yeah.
So you iterate the step 1 to 5.
Yeah.
And then until the difference is less than some threshold values. So will this difference always decrease, or is this a monotone decreasing function, or?
Yeah. So in our experiment and in our simulation study, like it's always decreased. Like we don't have like some diverge like kind of situations.
Why I mean, could you intuitively explain why it's like always decreasing?
So I would say like because we're not like using some gradient method here, right? So and all the like update is close form update, like a close. So I don't think that there will be like some divergence happen in the.
Okay.
But like yeah, it's a good point. Like we haven't like investigated much into why it's not diverging.
And so one thing, what's the superscript with small I means?
The iteration, like ith iterations means. Like in I step, like so the subscript, like the superscript, like I means that so in each iteration these parameters will be updated. Yeah.
But I mean, if your estimate is all admits the analytical form, why you need this iteration steps?
Because so once we first we get like a detrended noise. And that determinant is maybe like not very accurate because
Okay.
the estimation of mu t is not accurate.
Uh-huh.
And the idea of the generalized least square is that you update each time with the new estimated covariance matrix, and you get a better estimate of the trend.
Okay.
So the better estimate of the trend gives you better estimate of the residuals. And better estimate of residual then,
Oh, I see.
yeah, that will contribute to the estimation of the
Okay.
trend. So there's kind of like some kind of improvement in each iteration.
Okay. Okay, good. So
Yeah.
Yeah, so in this algorithm, like, have you empirically observed like whether the P change across iterations?
Yeah, it's, sometimes it will change, but
So when it change, like, do you still able to actually have this monotonicity of the error? Because usually that jump might lead to like changes, because you essentially change to another model. So
yeah,
I mean, we start like the whole learning again. Usually, I mean, like for some of these variable sections, like included in like the iterative error forms. When the model got selected, when the model change due to the selections, you might actually experience some jump, like in your in the error in that convergence criteria.
yeah.
Just curious, like maybe whether that actually happened.
I didn't observe this kind of behavior, but maybe because the ECG data like we apply on is like not very, so the error estimation might like is very stable. It's not will jump, but yeah, if it jumps then it might cause some problem. And
I guess it would be interesting to see like in the simulation setting where like it's not as easy to choose P. But for example, like two or three adjacent values of P's are like they are quite similar in terms of like maybe the criteria, or it's just difficult to pick. If there are challenges of that, it could be interesting to see like whether the algorithm would jump around. But of course, like I guess the BIC penalty will always favor the simpler one. Yeah, but it will be interesting to see something like this. Yeah, but, yeah. Thanks.
okay, so I think this week we'll have a fall break, and I think our next cafe will be after 2 or 3 weeks. So enjoy the fall break, and I know maybe some of you have midterm, so good luck on midterm, and during the whole weeks. Thank you.
请暂停 recorders，我没有。
Best second ever.
停了已经。
It's fine. What's Friday? That's like all.
Thank you.
I thought you were planning to